Hello everyone, you are welcome to my channel, Messed Up Mentors. This is Python for All, PY4A. In today's video, we will talk about array multiplication. Remember in our previous lecture, lecture number 22, we talked about array operations where I introduced array multiplication. But in this video, we will go deeper, okay, and here dive more into matrix multiplication, or what we earlier introduced when we talked about scalar or dot multiplication. There are two ways to perform array multiplication in NumPy. The first way is the element-wise multiplication, and this is done using the NumPy.multiply, or you can use the multiplication operator in Python. It takes two arrays as input and returns a new array where each element is the product of the corresponding elements of the input array. So that's why it is called element-wise multiplication. The second, okay, is what is known as the matrix multiplication, or in some paradigm, it is called scalar multiplication or dot multiplication. And this is done using the numpy.mathmul function, or using the at symbol, okay, or at operator, or using the dot operator in Python. It takes also two matrices or two arrays as input and returns a new matrix or a new array, which is the product of those two input matrices or arrays. Actually, in Python, we prefer to we refer more to arrays, or use the concept of arrays rather than matrices. For example, we'll firstly import NumPy as NP, and then we create a 1D array A and B, and then we define another array C, which is now the multiplication of A and B. So we have np.multiply A comma B. Okay, if we print C, what does it give us? It returns 4, 10, 18. Here we have element-wise multiplication of A and B. There are some instances where the two arrays don't have the same dimension or the same shape. What happens is that NumPy automatically what broadcast those two arrays based on what we learned on broadcasting in our previous video, lecture 23. It simply broadcasts those two arrays to have same dimension before it performs the element-wise multiplication. Also, you can use the Python multiplication operator, okay, asterisk, and then it returns the same outputs. The rules for array multiplication in NumPy are: if you are dealing with element-wise multiplication, the two input must have same shape. Okay, otherwise, if you have different shape, NumPy broadcasting takes place to make them of the same shape. The output array will have the same shape as the input arrays. Okay. And then the third one is that each element in the output array is the product of the corresponding element of the input array. That's why it's called element wise. They are multiplied element for element for element, in those two corresponding arrays. The second one is on matrix multiplication, okay, or what is called scalar multiplication or dot multiplication. Here, the number of columns, you have rows. The shape of every array or matrix is put in a tuple, rows and column. So here, the number of columns must be equal to the number of rows in the second array. And also, each element in the output array is the sum of the products of the corresponding elements in the two arrays. We'll see an example very shortly. So, for example, if you have an array n by k being multiplied by k by m, the number of column of A of the first array must be equal to the number of rows of the second array to give us a resulting array of n by m. Or we have n by p by k multiplied by k by m. The value of k here must be the same as this to return n by p by m array. For instance, an array of shape j, an array j of shape 2 by 2 by 2 being multiplied by k of 2 by 2 will return an output of 2 by 2 by 2. Note, broadcasting, like I mentioned earlier, can be used to relax some of these requirements. For example, broadcasting can be used to multiply a 1D array by a 2D array or a 2D array by a scalar. What it does is that it simply broadcasts the 1D array and makes the same shape as 2D array before it is being multiplied. Or it broadcasts the scalar to make it same shape as the 2D array. Now, let's go further by looking at this next example. Here we have an array E, which is a 2 by 2 array. Okay, we have F, also a 2 by 2 array. Okay, the element type or data type is float. You can see 10.02. So now let's assign G to the np.mathmul E and F. Print G and the shape of G. What do we have? G returns to us a 2 by 2 array, which you can see from the result printed. Okay, let's proceed further again. Here we also have another array again, J, which is what in this case, J is what is a three-dimensional array. Okay, and K is a two-dimensional array, right? First, let's print the shape before we multiply this. Okay, let's multiply before we print. Let's print first the shape of what of J. So we print J dot shape, and then we print K dot shape. If you run these, after that we print M. M is a matrix multiplication of J and K, and then we print the shape of M. Running this cell, what do we have? You can see that J is a 2 by 2 by 2, and K is of shape 2 by 2. So you can see that the number of rows of J is equal to the number of columns of J is equal to the number of rows of K. So that when you multiply it, what does it return? It returns a 2 by 2 by 2. Always bear in mind that before you can do matrix multiplication, either of these two rules must be adhered to. Otherwise, NumPy will throw up a value error uh, indicating a mismatch of dimension. Let's see another example. Here we have an array C. Here I just generate a random number, okay, with dimension 6 by 5, and D also generate number randomly with dimension 5 by 12. So I'll call the np.random. The random is a package, okay, in NumPy, rather a module in NumPy. So I'll call np.random to call the random function instead to generate random numbers of shape 5 by 12. So F becomes np.mathmul this, or like I mentioned earlier, instead of using this, you can use c.d. Or instead of using that, you can use C and then the at symbol D. Any of these will give the same results. We talked about that in video 23. I showed you examples of it. Okay, so let me use C dot D. And then first of all, before we print the output of F, let's print the shape of C, shape of D before printing the output shape of F. So running this cell, what we have, dimension of first input array is 6 by 5, second input array is 5 by 12, and the output of this F will give us what? Will give us 6 by 12. Okay, 6 by 12. In the same vein, also here, let's see what happens here if I have a 6 by 4 randomly generated array, which is C, and a 3 by 4 randomly generated array, which is D. Okay, first I print the shape of the first array, the second input array, and then do a matrix multiplication of C and D and assign it to what? F. And then let's see the shape of F. If we run this code, what do we have? It tells us the dimension of the first input array, dimension of the second input array, but what happens? It throws up a value error. Now, what do you see here in the value error? We are being told there is a mismatch in the dimensions of this array. Okay, we have an n times k, okay, being multiplied by k by m. But mind you here, this multiplication is not element-wise multiplication. Rather, it is what? It is the matrix multiplication or the scalar multiplication or what is also known as what? The dot multiplication. So it's telling us that size 3 is different from size 4. In other words, it's telling us that this value here, 3, is different from this. If I return this as, if I come here and return this as 4, and we will run this code, what happens? It gives us 6 by 4. If parameter this code becomes 1, I have a 1 by 4. What do we have? It simply gives us what? Running this gives us the same value error. So whenever you have a mismatch of dimension, it will NumPy will always throw up this mismatch error, especially with matrix multiplication. There is also another array multiplication I would like us to look at, but I will treat it specially in a separate video, and that is what we call the Einstein summation. Okay, it is very very useful when we get to deep learning, and then we can use that especially when we're talking about the language model, the attention mechanism. You will see the use of the Einstein summation. I'll do a separate video on that after my video on error handling. With this, we have come to the end of this video. If you like this content, please do leave a thumbs up for this video. If you have any question or you feel there's anything you want me to shed more light on or to discuss, please leave it in the comment section. Subscribe to my channel and do well to hit the notification bell to get notified whenever I upload new video. Until then, I will see you in my next video. Bye.